Hello everyone, and welcome back to another mathematics tutorial. Today I'm going to talk about connected spaces, okay, so connected topological spaces. So this does rely on you knowing what a topological space is. If you don't know, then I suggest you read up on that first, and then come back to this video. But if you do know, we can get started. I've got some text on the screen, but before we look at that, let's just think about an intuitive description of a connected space. So essentially the idea is you can't split the space into two pieces. So you can think of, say, a piece of string. It's just a nice long piece of string, but if you chop it in half, it's no longer connected because you've got the two separate pieces. But when you put them together and you join them all up, then it's the whole piece of string and it's connected. So essentially you just want it to be a connected line. Now, we need a sort of a rigorous definition here. So if we look at the text, I've taken a topological space, capital X and capital T, and we say X is connected if we cannot write it as the union of two non-empty, disjoint, open subsets of X. So let me just write that in slightly more mathematical notation. So i.e., we cannot write X is equal to A union B, where A and B are not empty. A and B, oh, I've made a slight slip of the pen there. A intersect B is empty, so they're disjoint. And A and B are open. Okay, so connected means we cannot write it as the union of two non-empty, disjoint, open subsets. Okay? Now, it's important to remember that open here means open in the topology capital T. Okay, so you have to be careful. If you've got a lot of different topologies on X, you need to be careful which one you're talking about when you use the connectedness. Okay, and often in any textbooks or notes you might have on this subject, they won't explicitly mention the topology, so you just need to be careful if there's more than one. Okay, now what about an example? Well, let me just separate this, and I'll give you an example, which is going to be quite an easy example. So e.g., it's going to be the indiscrete topology. So indiscrete T is equal to X and the empty set. So this is the indiscrete topology. The only open sets are X and the empty set. Is it connected? Yes, it is. Hopefully you can already see why. But if you just look at the definition, if I try to write X is equal to A union B, where A and B are open, then I only have two choices. I can have X or the empty set for each one of them. But now this is a problem, right? If I take the empty set, then they're empty, which is a problem because we're looking at non-empty sets. So I'm left with X as the only choice. And yes, I can write X is X union X, but if X is non-empty, then it's not going to be disjoint because X intersect X is just X. So if X is not empty, then this is non-empty, so they wouldn't be disjoint. And obviously if X is empty, then we have the same problem of, because I insisted that A and B had to be non-empty. So you can see that there is no way to write it as a union, A union B, where A and B satisfy these conditions. So the indiscrete topology on a set X is connected. Hopefully you can see that. It's quite a straightforward example because we've only got two sets to think about. What about some less trivial examples? Well, there are quite a few. Let me just erase all this. I wrote quite a bit there. Hopefully you took it all in. So let's look at some non-trivial examples. We can take the real numbers, So R is connected. I will do a proof of this in a different video, but for now, just take my word for it. I mean, you can think of the real numbers as just a infinitely long line, can't you? It's just a connected line, so you can kind of guess it would be connected. What else? Well, 0, 1, the open interval 0 to 1, is connected too. Again, I will do a proof in a later video, but you can just think of it as that, can't you? It's just that line from 0 to 1, and it's clearly, it visually looks connected. So you would hope that it would be true that it's connected. What about some disconnected sets? Well, let's have a look. What if we take, let's say x is equal to 0, 1, and then I'm going to union it with 2, 4, so 2 open intervals here. This is disconnected, well, I shall say not connected, but disconnected and not connected are the same thing. So this is not connected. Why? Well, it's kind of immediate, right? If I take A is 0, 1 and B is 2, 4, then we have A and B are not empty. Indeed, there is at least one point in both of these. A intersected with B is empty, so they are disjoint because you can see the intervals don't include each other. And A and B are open. Good. And X is, literally by definition, X is A union B, because I wrote it as the union. So this is not connected because we can find two sets A and B that satisfy the conditions, and X is the union of the two. So this is what I want to illustrate. If it's connected, you can't find two sets like this that work. And if it's disconnected, if it's not connected, then that means you should be able to find at least one pair of sets that satisfy the conditions and give you X being equal to the union. One thing that I didn't mention is what topology was I considering on X. You know, what is the topology T here? And naturally I was taking the usual topology on the real numbers, the standard topology, if you think of the real numbers as a metric space. So when you're writing questions like this, or when you're writing answers to questions, do make sure you check what the topology is. If it's not stated what the topology is, then they probably mean the obvious one. So if it's the real numbers, they just mean the normal topology. But you do have to be careful. So it was a bit sloppy of me not to mention that. What else? Well, there's not too much else to worry about for now. The only other thing is there are a couple of other definitions which are equivalent. So I'll just go over one now very quickly. And that is, let me just put equivalent up here. So this is equivalent to the connected definition. The only Clopen sets, so Clopen means closed and open. The only Clopen sets are X and the empty set. Why is that the case? So to see this, we can write X is equal to, say, A unioned X without A, X minus A. So this is the complement, the points that are not in A. Now, if A is Clopen, that means A is open. So when A is Clopen, we have the A is open. And x minus a is also open because a is closed and open. So when it's closed, the complement is open. So we have that a and x minus a are both open. So unless they are x and the empty set, we have a problem. Because so we're assuming x is connected here. So I insisted that the two sets had to be non-empty and disjoint and open, etc. So unless we take one of these options, we have a problem. So this is equivalent to connected. The only clopen sets are x and the empty set. I would encourage you to prove that this is equivalent on your own. So this is sort of a sketch here of how you can do it. Hopefully you can see what to do. If not, do leave me a comment and just comment on this video or send me a message or something, and I'll put up a video with a more detailed proof with all of the steps. But hopefully you can see what to do, and it'd be a really good exercise in the definition of connectedness. Okay, that's all I wanted to say for now. There are a few more videos I'll be doing on connectedness. So the next one is going to be on another equivalent definition, which is quite useful. And a few other things. So do keep an eye out for those. Don't forget to subscribe and leave a like and a comment if you found it helpful. Bye for now.